on to the p orbitals. Okay, so when we have n is equal to 2, we can have 2s, which we just described. We talked about 1s, 2s, and 3s. But when L is equal to 1, we can have 2p. Okay, and I made note that because there's 3 ml numbers, that gives us 3 orbitals. So thus we get 3 p orbitals, and here they are, 2px, 2py, and 2pz. We could also have 3px, 3py, 3pz. We could have 5px, 5py, 5pz. We could have all of those, okay? We could definitely get into those. And we can definitely have nodes, radial nodes for these. But what we're also going to see, in addition to having radial nodes with the p orbital, there's also angular nodes. So I'm going to try to draw here the difference between those two. Okay? So now if here's my p orbital, all right? So as it turns out, let me do a different color. Okay? So this area right here and this area right here that's empty, so I'll say like this and this angle theta and this angle theta, those represent an angular node. And we're going to calculate how many there should be, okay, in a moment. So how do we represent radial nodes? Well, the radial nodes are going to be internal. Just like we saw with the s orbitals, those radial nodes make those internal nodes, okay? Well, as it turns out, p orbitals can also have these types of onion shells, okay? So 2p, so we have to kind of inspect here, are they going to have any, and what is that going to be, right? So for 2p, we recognize the total nodes will be 1, because it's always n minus 1 for the total, and n minus 1 minus L for the radial. All right? So for 2p, that's 1 total node. But what about the radial nodes? Well, n is equal to 2 and L is equal to 1. So 2 minus 1 is 0. So 2p has 0 radial nodes, okay? So that means 2p's only node is angular. It just has 1 angular node. And I know when you're looking on here, it looks like there's 2. But this is represented, so they're the same angular node. What it really does is it makes like a stair radian. It makes like a solid angle, okay? So 2p only has 1 angular node. Well, what about 3p? Okay. Well, we know 3p has 2 in total, right? Okay. It has 2 total nodes. So how many radial nodes will 3p have? Well, it's going to have 3 minus 1 minus 1, which is 1. So that means 3p has 1 angular node and 1 radial node, and this is it. So this is a 3p orbital that I'm showing you right here. And so these, these solid angles, these discluded areas that I've indicated, those are your angular nodes. The radial node is internal. And we'll see that on a graph here in a moment. But what I want to switch to is my Mathematica simulation here that I have my 362 students do. And so here we go. Here's the 2p orbitals. Here's all of the equations. And so this is the calculation of the 2pz orbital. Okay. This is the calculation of the 2px. Oop, it got small when I flipped it around. Here's the calculation of the 2py. And here is now putting them all together. Okay? So when we put 2px, 2py, 2pz together, it does make this pretty cool shape. It is this 3-dimensional shape. And we're going to see in Chapter 8 how this shape will manifest into the shapes of a molecule. So for now, this is just what a random electron would look like in a single atom. But this will get connected. We will connect this to how this determines the shape of molecules, which is pretty cool. Okay, so here you can see that on this slide as well, right? The 2px, 2py, 2pz, and then the total view of all of them together. Okay, so if we look at the radial profiles of the p orbitals, okay, then here's where we're going to start to see some interesting stuff. Okay, so we noted that nodal plane is part of that angular node that I was talking about. It's part of that discluded area, okay, from the two lobes. And so if we were to look at the graph now, if we look at 2p, for example, we notice here 2p, the red curve, it does not have any radial nodes. So 2p equals 0 radial nodes. And we see that on this graph, right? It's just one peak, all right? What's also interesting, what we're going to start to see as well, is when we start putting these probabilities together with 1s, 2s, and 2p, they all start overlapping with each other. And that's going to create electron interference. So a 2s orbital will definitely interfere with a 2p orbital because they're similar in size. So they have their most probable positions in a very similar location, okay? But we also notice that the nodes, so now the green curve is 2s. We also notice now, because of those nodes, we can distinguish on these types of graphs what orbitals they are based off of these two equations, okay? So like, for example, I note that 2p should be very close to 2s because they're both level 2, so they both should be very close. However, 2p will not have any radial nodes. However, 3s will, okay? So we're going to see more of this stuff when we put together the remaining orbitals, all right?